Hello and welcome to Extreme Academy Live, Part 3. Thanks for joining the live session. In Part 1, we covered bits and bytes and binary and how data is transmitted across all of our systems as electrical pulses. And then in Part 2, Isaac introduced you to the OSI model and how there is a framework for how data is transmitted and communicated based on rules that have been created just to make sure everything works smoothly and all the different equipment and software can interoperate together. Now we're going to be spending more on that today. Then we're going to have a break for the holidays, and when we come back in January we're going to be getting into wireless communication. We're going to be demystifying the magic of wireless. So Isaac's going to take you through how data is transmitted in exactly the same way using very similar rules, but it happens over the air, so the physical medium is actually radio waves. Then beyond that, we'll broaden out into network management, and we'll be talking about cloud networking. And that's the thing that, all of us, all the Extreme team working here, that's what we're doing day in, day out, working with customers and our partners on how to harness the power of the cloud and the analytics that come from it with regard networks. Now, I mentioned OSI, and you've been hearing about OSI. I wanted to clarify one thing before we get going. So this is Ozzy, the owl. He's our mascot for the Extreme Academy, and Ozzy is short for Oswald. It's not short for OSI. We didn't name Ozzy after the OSI model. I just want to clarify that because somebody did ask that on a question last week. Now I tell you what, it took absolutely ages to get him to stand still and pose in that little hat, but hats off, literally hats off, thumbs up to our marketing team. They managed to get that photo. Now we'll have a bit of fun with Ozzy. There is a video right now on YouTube where you can have a staring match with Ozzy the owl, and owls, as you know, are very good at not blinking. So if you want to have a bit of fun, you can go and find that video on our YouTube channel, and we'll put the URL up for that during the break or some point during that session, just in case you can't find it. So same drill as before. If I think over my shoulder there should be the Q&A QR code, so you can go in there and ask questions. You can take some quizzes just for a bit of fun, and if we change anything in there, because that is a tool we can change over time, we'll put a message up there, or we'll send a message to you through that app to let you know that there's some new features there as we go along. Now, usually I have a little monitor next to me, just over here, where I can see Isaac, but I couldn't get it working today. So I know he's there. Claire and the team have messaged me. I know Isaac is ready to go. I don't know if he's wearing a hat this week. You'll find out at the same time as me. And I've noticed Isaac has been moving things around on his shelf. So maybe you can spot something that might have changed since last week. So we're ready to go. Hope you have a great session 3. And Claire, want to bring in Isaac? Let's go.
Hey everyone, how wonderful to be back again for week 3. Thanks, Rowan, for that intro. What can we say? We started this as a project to help people, to train people. Our target was 50,000 people, to reach 50,000 people. The views on YouTube, the views on Vimeo, they just keep going up week after week. It's so exciting to see. It's wonderful to see, to read the comments. Lots of comments on YouTube. Lots of comments that have come in using the survey that we sent out. Thank you so much. There were wonderful comments there. It's really been lovely to be able to do something like this, to be able to help people. I've received emails, we all have, I think, of the impact that this is already having on people. So it's absolutely wonderful. I'm so delighted for what we're doing through Academy, and that you are being helped and that you are learning. There are many people like me on the internet doing training. There are many people teaching, some better, some worse, but everybody has something to offer. So I really encourage you, don't listen to just me, listen to other people as well, so that you can get a really well-rounded message. What else is there to say? Well, today we're going to cover some really important bits of the OSI model, right? We've we've done already quite a bit, right? If you think about where we were lesson 1, not knowing anything about networking or very little, we've moved to lesson 2. And lesson 2, we primarily cover the whole or most of the OSI model. So we know we've covered level 1, which was the physical layer, right? We know we've covered that. And then we did layer 7, 6 and 5 and 4. So we did those top 3, the applications, where we saw how browsers and things like that manage to do stuff, and that was very interesting. I really enjoyed teaching that. But the heavyweights, the real networking guys, they focus really on these 3 layers: layer 1, layer 2, layer 3. Layer 2 and layer 3, they really are the layers where stuff happens. When it goes wrong, that's where they go and look at it, right? If your browser's not working, you don't get a network engineer to come and look at your browser. If your browser's not working, you just fire up another browser and it works, and if it doesn't, it's probably your internet connection is down. But when an office cannot communicate with another office, when no one on a telephone network, an IP telephone network, can communicate outside of the company, that becomes a problem. And that's when these guys come in, the network guys come in, and they start looking at these 2 layers. Okay, so what is the problem? Are we able to send a print job to the printer? Does it work? Does the printer come back? Does it give us a printout? Does that happen? Or for example, printing works fine, but anytime we try and get something outside onto the internet, that doesn't work. And then that immediately tells them this is a layer 2 or a layer 3 problem. And so that's why network engineers focus a lot of time here. And today we're going to do the same thing. We're going to focus a lot of time, probably the majority of the time, or maybe the whole first session, we'll be talking about layer 2. So let me just check. We got 50 minutes more or less to go with this, so I know where I need to go. So once again, coming to you from Cambridge, the city of an amazing university and amazing scientists, right? Now, I've got some emails about, Newton didn't invent gravity. Yeah. Sure. But another really famous scientist that came out of this area was, of course, our friend Mr. Darwin, right? And here in Cambridge, Mr. Darwin invented revolution, and it was quite an incredible thing at the time. It really broke a lot of traditions and a lot of thought, and he was really a thought leader. So that is just another one of the very famous scientists. And if you ever come visit Cambridge, you can go to the university, and you can actually go. They've actually dedicated a little bench where he used to sit when he was thinking up these theories on revolution. And there's a little bench there, and you can have a photo with taken with you. I've got one of those. So really, if you come to Cambridge, you got to come through to the university and go and see where Charles Darwin came up with his theories. So let's jump in to layer 3. And once again, I'm going to read the objectives of the course, because it's easier than just to try and memorize all of this. So what we're going to try and do is understand the principles of the networking layer, the network layer. Understand the addressing that works on this layer. Understand routing. Now, we say in the UK, in South Africa, we say routing. And I know for my American friends, for the American audience, you say routing. Routing, call it what you like. It's spelt the same way. So I'll call it routing. You know exactly what it means. And then the fourth part is to understand the different traffic types on layer 3. So, network layer. Conceptually, this is going to take a little bit of mental gymnastics, and I'm going to try and paint as many analogies as possible, because this was one of the things where I found quite a lot of difficulties in understanding this layer 3. But again, I'm quite confident that we can get through this. So networking layer is where what we call logical addressing is separated from physical MAC addressing, or let's call it when logical addressing happens. Now, already there, I'm using a term that you might not be familiar with. Logical addressing. Logical addressing. So, in the previous session that I did, I mentioned at some point in time about how every hardware device that connects to the internet, from an IP camera to your computer, to your little router, to a little access point, to your fridge that connects to the internet, to your bath that connects to the internet, to your sleep mattress, sleep blanket that connects to the internet. All of those devices have what we call a hardware address. Another term for it is a MAC address. Now, remember that MAC address has got nothing to do with the company Apple, right? It's not an Apple address. Apple devices also have MAC addresses. Windows devices have MAC addresses. Linux, any device that you have has a MAC address. This probably has a MAC address. My watch has a MAC address because it connects to the internet. And we said those are permanent numbers that are marked on these devices. Someone in the conversation in the chat window that we had last week used a fantastic example. I don't recall who you were, but well done. You used a brilliant example. You said, if you think about a vehicle has a VIN number, VIN number, and I think that's universal because I remember seeing those in South Africa, and that means that on the actual chassis, on the actual body of the car, I think it's actually on the engine, it might even be on more than one place, they have stamped a number when that car was made in the factory. That's a unique number that identifies that car. When the car is sold, when you purchase that car, you get a license plate, a registration number. That registration number could change, right? It could. If it goes to another owner, if it gets sold and goes to another country, it could get a different registration number. But the VIN number is always the same. And the same thing with hardware addresses, with these MAC addresses. They are stamped onto the device. By logical over here, what we're talking about is the address, the registration plate of that car. Is that okay? The registration plate. So the car has both. It has a MAC address or a VIN number, and that never changes, and it's got a registration plate, and that could change as it goes from owner to owner. I mean, in the UK and in South Africa, you can say, I'd like to change my registration plate, and I'd like to call it Isaac, ISAAC, and they charge me X amount of pounds, and I can have my own customized registration number. Doesn't change the VIN number. Still that same car. It's still that special identity that's been plugged onto this. And so that's how it is with laptops, for example. Your laptop has a MAC address. Now, if you're at home, you have an IP address. Apart from the MAC address, that's permanent address, you also have an IP address. We call that the logical address, a registration plate. You have that on your machine. And it's given to you when you switch on your machine at home, right? You have a little wireless access point or a router that connects to your ISP, and when you switch on your machine, if it's a wireless laptop, it connects to that router and it gets this logical address. It's not permanent, because if you take that machine and you go off to a coffee shop and you fire up your machine, it will then get a logical address from the coffee shop. The MAC address stays the same, but at the coffee shop, it will get a new address. And then if you're going to go travel and you go to an airport and you're sitting in an airport lounge and you fire up your laptop, guess what? It's going to get a logical address from that wireless network at the airport. So I hope that that explanation is okay. For some of you, this stuff might be really, simple. If you're a qualified network engineer, this stuff is way, you've done this stuff years ago. You know the stuff off by heart. So, don't say on the comments, oh, this is too simplistic. It might be for you, but for a lot of people that are watching and listening, it's really useful. So it's very important that we understand IP addresses and logical addresses as opposed to physical addresses. Layer 3 is about logical addresses. When we go a step down, closer to the wire, we talk about layer 2, hardware addresses. And that's where we cover hardware addresses a lot more. So logical addresses, they help us to reach beyond our local network. Okay, so think of it like this. This is another way. A logical address allows you to get onto the internet outside of your local area network. Inside your local area network, you use physical addresses to go from this machine to that machine, from this machine to the print. You use physical addresses. But on the internet, you use logical addresses. So I think I've mentioned in the last one, I like to think of the analogy of a passport. In South Africa, we have two types of identity documents, right? We have an actual document called an identity document. It's got a number, unique number, and it has a photograph. And we have passports as well. Yes, of course, we have driving licenses and those things, but officially, you can use your ID for anything that needs to be done within the country. So you need a document, you need to, report an accident, whatever, you use your ID, your identity. It is useful inside the country. If I come to the UK and they say to me, can we see proof of who you are? If I try and show them my South African ID, they'll say to me, I'm sorry, that doesn't apply here. We don't recognize that. But it's got my photo in it and my ID. I say, yeah, but we don't recognize that. That doesn't work over here. But a passport, if people in South Africa ask, we want to see some form of identity, if I take my passport, they will accept that. But the magic of the passport is, in South Africa, the ID is only for local, right? Only inside South Africa. If I come here to the UK, if I have the passport, they will say, oh, absolutely, that's fine, no problem. You can come in through the border, everything, you've got the passport. So a hardware address used in a local area network, in a boundary. We sometimes call that a broadcast domain. A passport, a logical address, that allows you to get onto the internet. That allows you to travel. That allows you to go to another country. And when you get there, you show them the passport and they say, absolutely valid, you can come through. Or like the UK says, no, you can no longer come through after Brexit. But that's another issue altogether. So I hope that is clear. And in this next illustration over here, I'm going to try and show you. Let me just try and get this this laser pointer to go green, and then I can show you what we're trying to do over here. So here's typically what I would want to do, and why I would need a logical address to communicate if I wanted to do this on the internet, right? I'm sitting at home, I'm on my PC, let's call it PCA, network 1. I'll give my network a name. I could call it Isaac's home network, Isaac's LAN, whatever it might be. And I would say something, this is an analogy, an example, right? Operator, I'm Andrew from 142nd North Avenue. Please deliver this message to John, right? And John lives at 23 East Drive. Okay, so that could be a absolutely perfect normal type of conversation. And my router, my little box, is going to look at that and say, oh, okay, you're living here. but the message you want to get is not for here. It's 23 East. That's not here. That's not your street. That's somewhere else. So the router says, okay, I'll try and deliver that using the logical address. It then says, well, I don't even know who this person John is and where it is. I really don't know. But I know that Frank operates kind of in that region. Okay, so I'll ask Frank. Maybe Frank knows how to find John. So he calls up Frank. Router 1 calls up Frank and says, hey Frank, you deliver to East Drive, right? Is that where you deliver to? And yeah. Router 2 on the other side of that says, yes, I do. I deliver there. It says, well, John from 23rd East, he wants to send to or Andrew wants to send to. Oh, I'm getting confused with all of these names. Just read it on the screen, right? But you get the point. Me, Isaac, Andrew wants to send to John. He's got a message. Can you please send it to him? And then on PCB, on the other side of network 2, says, yeah, I've got something to go back as well. So you see the process that's flowing. If I want to talk to a printer, I don't have to talk to the router. Right? I don't have to talk to that little black box that sits there, in my lounge connected to the internet. Why? Because that only deals with traffic that needs to go outside of my network onto the internet. If I need to print, no need to go outside. I can print internally just using the MAC addresses. Now I know there is a mapping between MAC and IP, but you get the idea. Internal, we use MAC addresses. External, we use these logical, or what we call IP addresses. Okay, so let's talk a little bit about IP addresses, because I've used this term quite a lot and I don't like talking about things and just assuming that people know exactly what I'm talking about. IP addresses. Well, an IP address is just like a phone number, right? Without a phone number, you can't dial someone. It's as easy as that. That's what an IP address. It looks a little bit different, but we'll get to that. We'll get to that just now. But IP addresses, they have information in them. So they don't just have a number in them. They have headers in them. Okay, and those headers, an IP header has information, certain IP addressing. It's got when I want to send this packet to somewhere, so it will have a destination address, right? So if I want to send something to John, okay, then it has to have the John's address, the destination address. It also has to have a source address. If I receive a letter from somebody, generally on the back of that letter it tells me where the letter is coming from, the source address. On the front side it tells me the destination address, and that's of course provided, the source address, by the provider, the person who sent the envelope or the mail or whatever it might be. Each address also has something we call an associated network mask. Now, network mask can be a little bit confusing, and I want to do a bonus lesson on that, and I'll maybe post it during that period when we won't be transmitting over this festive season. I'll put some bonus lessons up. There's already one there called DNS. I think it went up. Or is going up today. I recorded it. I think it was last week, and that's going to go up, and that's really an interesting one. You're going to learn about DNS and why my mother is better than most DNS server. In fact, all DNS servers out there. Watch that video. We'll tell you about it a little bit later on. But I'll do some more on subnet masks because they can be quite a confusing thing. But an IP address is a logical address. It's normally tied to a subnet mask, which is another type of address which has a really special function. And its function is to identify which network you are on. So think about it. It's not true, but completely true, but think about it as the network mask being the house number. Okay, just think of it as being the house number, or the street on which you live, right? So you have, for everybody in the street in which you live, every one of you have separate addresses, yes, but the street is common to all of you. So if I wanted to deliver a letter and that letter said this particular street, then that would be easy. I say, oh, okay, just, when I'm sorting out all the letters, just bunch them all together by the name of the street. And when I get to that street, if I'm a postman, when I get to the street, I'll just pull out all the envelopes that are destined for that street. And I'll go, oh, okay, you number 1, you number 2, you number 3. So it's a way to identify a network, for the computer to identify it. And it's important because that router needs to make the decision whether is this package for the local network, for Isaac's house, or is it for outside the network? How else would it know? It doesn't know. It doesn't know all the MAC addresses of every device on the internet. It's impossible to know. So it looks at the subnet mask and that identifies, oh, this is Isaac's network. This is internal. No need to go to the router. I'll just send it directly to the printer. Okay? So IP addresses are divided into 4 parts. And this now should be really easy for you if you have watched the first episode that we did, the first lesson that we did, where we spoke about binary. You remember? We spoke about binary and we said 8 bits makes up 1 byte, right? 8 bits makes up 1 byte. An IP address is made up of 4 bytes, okay, separated by a period or a full stop, okay? So 4 bytes, 32 bits. Why? Because each byte is made up of 8 bits. So on this example that you see on the screen, 192 is a byte, 168 is a byte, 1 is a byte, and 250 is a byte. Okay? You should in your head already have the ability to go and work out what these bits are. If I were to say to you, what's the binary of 250? You should say, well, I know that the maximum that they can go to is 255, and I know that for it to be 255, it'll be 1111111. That would be 255. But if he's asking for 250, then there's a 1, 2, and a 4, so it would be 1111101, something like that. something you work it out. My brain is just not engaged to do this calculation, but you get the point, right? The second byte, the 1, well, it would be all zeros, and then the last bit would be a 1, correct? Absolutely. So you see what happens? You see how useful binary is? IP address is made up of 4 bytes. Now think of about a mobile number. A mobile number generally has your international dialing code. So in the case of mine, it's got +44, right? And then it's got, generally 3 digits and then maybe 4 digits after that, okay? And that's the format of a mobile number. Well, IP address has a format, but it has to be written in this way, okay? You can't have 3 bytes. Nope, that doesn't work. You can't have 7 bytes. Nope. IP address is standardized like this. Now, when I say it's standardized, what I mean is for many, many, many years since we first began using the internet, we had a version of IP addressing which we called IPv4, IP version 4. And IPv4 was made up of 4 bytes. Now, we ran out of addresses. right? We ran out of addresses a few years ago. We still all have them, but there are so many millions of devices coming on stream all the time. We couldn't make numbers that were big enough. So now we have something called IPv6, and instead of 4, it goes to 16 bytes. So now we have literally hundreds, gazillions of IP addresses, and hopefully we will never run out of addresses on that. We might, but it's massive. It doesn't you're right, it's slightly different to this, but I'm going to use IPv4 throughout this course, so just stay with me there with that. So divided into 4 bits, each one of them into 4 bytes in size, and we call this dotted decimal notation. There's another type of notation, and we'll talk about that. And each byte, of course, as you know, can range from 0 to 255, or from 1 to 255. Here you can see just a few examples, right? 255, 1 1 1 1 1 1 1 1. So 250 would be actually we would have 1 1 1 1 1. We would turn that one off, so it would be 0 0 1 0, something like that, because we would need to remove 5, and 5 would be one of these and one of those. So we have 100, 0 1 1 0 0 1 0, and there you have 11 in binary. So you see how binary is really useful in so many things that we do within networking. In days gone by, when I first started in networking, there was they used to talk a lot of, when they started teaching this, they would talk about different classes of IP address, and you had to remember what these classes were. And it started by talking about, class A, class B, and class C, and class, and I could never remember this. It's like, this is why at that time I absolutely hated doing networking stuff, because they tried to teach you things that's like, but somebody came out with a really neat way so that you can write what used to be written as Class A addresses. They found a really simple way, notation, a different notation, and they call it CIDR, not the stuff you drink, CIDR. You can see here on the screen, let me just bring it up with the laser, CIDR, Classless Interdomain Routing. So let's look at that. First we'll look at that, but let's look at what it really represents. This is the complicated one, and then the CIDR makes it easy. But let's look at this over here. So they would say a Class A address. You get a Class A address, and the Class A address would have 1 byte, the first byte, to identify the network, the street, your local area network. All right, it would use 1 byte to do that, and the other 3 bytes, they would identify the houses on the streets, or the house numbers on those streets. Okay, the devices on your network. So 1 byte to identify the network, and then 3 bytes to identify the hosts. Okay, now you can probably start figuring already that you don't have a lot of networks over here, right? You could have 128 networks, 126 actually, because you don't use 2 of them, but you'd have 16.5 million hosts. If you had a Class A address, you could literally have 16.5 million devices on the same network. I don't believe there's any organization in the world that does something like that. The amount of broadcast traffic on a network like this would be absolutely horrendous. But you had Class A addresses. 1 byte for the ID and 3 bytes to identify all the hosts. Not very practical. Okay, so let's look at Class B. Class B said, hang on, what we'll do here is, because Class A is so big, maybe the organizations who need that, let's make a Class B. And so a Class B, they said, okay, So let's identify the network with 2 bytes. Okay, so we'll use 2 bytes to identify the network, and then what we'll do is we'll use the other 2 bytes to identify the amount of hosts on the network. And so this is what you end up with. You end up with around 16,000 networks. You could identify 16,000 networks. So this type of class network, this could be given to a country. There's a body called IANA, IANA, and they are the international body that are responsible for assigning IP addresses and groups of IP addresses to registries in different countries. So they might look at this and say, okay, the UK has asked for a range of addresses. Maybe one of the big mobile telecom operators in the UK, O2 or Vodafone or one of these, they are opening up. They're going to start a new business, and they need thousands and thousands of operators. People on the network. So maybe what we're going to do is we're going to give them 10 of these Class B addresses, because each one can do 65,000 hosts, okay, and 16,000 networks. So we could give this whole range of addresses to one of these ISPs or to one of these mobile telephone providers, and you could see that they could have millions of users on their network as long as they're using this type of address. Do you get the picture what I'm talking about? Over here, this would be totally useless to have in your home. You'd never be able to get an address for your home. Like, why? You don't have 65,000 devices in your house, So that would be what we call a Class B. And then the Class C would be where we identify the network, the street, yes, with 3 bytes. We identify the street with 3 bytes. The network name, we identify that with 3 bytes, and then we leave the last byte giving us how many? 255. Not really. We lose 253 hosts, 253 computers. So you can see that this is quite useful, because you have a company like Extreme in Reading, and they might have, 150 people, maybe 200 people in the office. I don't quite know, but that would mean they could get an address like this, and everyone in the office could have an IP address, and they could have a few for printers and a couple for, for IP cameras and things like that in the office. Do you see how these things are useful? So Class A, Class B, Class C, and around about 2 million networks, 254 hosts, 253 to 54 hosts on a network. So hosts is another word. I don't want to say computers. Some people think, oh, host, why don't you just say computer? 254 computers on a network, because an IP camera is not a computer. It's a camera. It's a security camera. Fingerprint reader is not a computer. It's a fingerprint reader. A printer is not a computer. It's a printer, and it also has an address. So we rather use the term host. It's kind of a generic term that includes everything that has these addresses. There are also Class D and E, but these are generally reserved. They're not used. They're not used on the public internet. They're reserved for the research community, for universities and stuff like that. So this network mask that I told you about, when you set up a computer on your home network, you generally don't have to worry about an IP address, because if you've been sent one of these black boxes by your ISP, then in that black box there is a software tool called DHCP, Dynamic Host Configuration Protocol. In fact, when I say tool, it's really a protocol. And when you switch on your device for the first time, it will broadcast and say, hey, I'm here, can anyone give me an IP address and a subnet mask and all of those things. And that little box will pick up that request and say, oh yes, I've been told that you're on this network, okay, and I'm going to give you an address. So here's your address, and by the way, with that address I'm going to give you the street that you're on, the network mask to identify the street that you're on. Yes, the network that I'll send you that, and I'll send you other information like DNS server and all of that. I'll send you all of that stuff. It's not different to when you switch on your mobile phone for the first time. I recently bought a new mobile phone, and when I got the phone, I put in the SIM card, right? As long as that SIM card wasn't plugged into the phone, that phone was useless. You know, if it didn't have a wireless network in the area, the phone is useless. Yeah, you can take photos, but you can't communicate because it needs an address. So by putting in the SIM card or by connecting it to the wireless network, suddenly when I connected to the wireless network, it got all of this information. Its IP address, its DNS, it's got all of that, and suddenly I could communicate. So this DHCP sends all of that information out, and the subnet mask is going to look something like this, one of these two ways, either 255.255.255.0, right, which is a class C, but that CIDR notation, CIDR, is written in this way. Let me point it again with a laser. Look here, 192.168.1.1/24. Now you might be looking at that and going, geez, like, now he's confused me. /24. How does that? Well, look at it. /24. How many bits in 1 byte? 8. Correct? So in 3 bytes, 24 bits. Look here. 255, 255, 255, 0. 255, 255, 255. Class C. Every bit is switched to 1. Yes? So instead of writing it like that or referring to it like that, let's just make it easy. Instead of saying this is a class C address and people having to remember, we just say /24. The first 24 bits have been blocked out. The first 24 bits have been turned all to 1, so it's a mask that lies on top of an address, and we say, oh, okay, so on this IP address made up of 4 parts, the first 3 parts, the first 3 bytes or 24 bits have been masked out. That means that that's the street. That's the street. So everybody on this network is sitting in that same street. I've got 1 byte where I can have 255 houses on that. So it's a way to identify the network. Okay. With CIDR, CIDR, we use network mask, right? We call them subnet masks. So we call them a network mask. We also call them a subnet mask. So submarine, and net, and everybody knows about the mask in 2020. So it is specified at the same time as the address when configuring a device for layer 3 communication. Okay, so when you get to layer 3, right? Remember the data has been formed on layer 7, 6, and 5, and you've had the sessions, and you've had TCP/OU. All of that, port numbers have been added. When you get to layer 3, the network mask is known. That layer 3 will know, oh, on my local computer, when I checked, I did a call and it says, the network mask is /24. Okay, so now I know what is my address. Let me look at this address. Ooh, this address is from a different network. It's outside of this network it's outside of the street. It's on another street. It's in another country. I know I'm going a little bit slow over here, but it's really important that we understand this. So here you can see, right, 192.168.134 is an IP address, the logical address, and here is the subnet mask. In Windows, if you go to your control panel networking, you will usually see this type of information there. It always needs a network mask to identify. So this 255.255.255, or this represented as /24 means the first 3 bytes are all turned to 1. They mask out because they just represent the street, and then the 0 obviously in binary looks like that. Okay. So we know about this. The layer 3 eventually passes the information down, some information down to or information down to layer 2. Layer 2 then handles the MAC addresses and finding out where they need to go to. So I mentioned here in this last slide something called, right on the last point there, the MAC address, right? So there's a protocol, we call it an address resolution protocol. When I need to send, so this now will happen on layer 2. Now, I know we're talking about layer 3, but it's just, we need to just quickly step into layer into layer 2. This hardware address, this we need to map that address right to a physical address. We need to know a physical address because I said to you, internally we use physical addresses, these MAC addresses, to send data to. So we use the address resolution protocol to be able to do this. And this protocol, when it gets fired off, it basically says, hey, I am such and such a machine with such and such a hardware address, a MAC address, and such an IP address. Can whoever has the following IP address please respond with your MAC address? Okay, and it broadcasts. So the ARP shouts on your local network. Every device connected to that network will hear this shout out. It's as if you took a megaphone and shouted down the street and everybody heard. So you shout out with that ARP and you say, everybody on this network, can you please respond to me with your MAC address if your logical address is ABCDE? Okay, and that device, that printer or whatever, is going to say, hey, it's me. Let me show you an example. Okay, so we're just stepping in quickly to layer 2 because I'm going to differentiate in a few minutes between layer 2 and layer 3, or layer 3 and layer 2, why layer 3 is a little bit different. So here you'll see PCA. You'll see it has a MAC address, right? MAC address, the hardware address, and it has an IP address. You look at those addresses, you'll see they look a little bit different. I will explain that. So here's, it has an IP address that it got from the black box. It says I'm 192.168.10.125, and I need to send to the printer. Okay, so if we look at the header for this information, we say, well, I need to go to the printer. I don't know the printer's IP address. I don't know the printer's I know the printer's IP address, but I don't know the printer's MAC address. I am the source MAC. So this is my MAC address. That's that information there. Let me switch again the laser. That's that over there. That's where I am. I have a few other printers and machines and switches in my area network. Ether type, that just tells me, oh, this is Ethernet, right? This is IPv4 that we're using. My source IP address, well, my computer knows what's the source IP address. Its address is 10.125. There it is over there. And it knows the destination address of the printer, right? Because the printer, we got to that when we did the DNS resolution. Hey, who is the printer? And the printer said, it's me. This is my logical address. So it gave us its logical address. We know what it is. But on layer 2, devices don't talk using logical. They just use hardware. So I need to figure out what's the hardware address for this logical address. This part here we call the IP header. Okay, this is the header, and this entire thing we call the payload. Okay, the payload. So let's switch over and go here. So I send an ARP broadcast. I shout, say, hey, can the machine with the IP address, 192.168.10.21, can you send me your hardware address, please? Okay, and so here, there's the broadcast that I sent out, the destination MAC address, meaning I'm sending out, I'm shouting that ARP, that protocol sends out an ARP to all the devices on my network. Okay, so here it is. Everything has been turned to 1. This is the same as saying 255, 255, 255, 255. All of them. I broadcast all this information out, source MAC, etc. It's a request that goes out, an ARP request. This is the sender MAC, this is the sender IP, and I'm targeting everybody. Please, can you respond? Whoever is the right has that information. This printer says, hey, that's my name. You called out my name. My name is 192.168.10.21. Yes, I can actually send you that information. And what it does is it sends back its hardware address, its MAC address. It sends it back all the way back to this computer. And now you'll see it's a reply. It's no longer a request. Now what happens is I can now send the print job to that printer, right? Now that I've got that information, I can send that print job to that printer for it to go ahead and print and walk over and go and get that information. So on the layer 3 network, we only talk about the logical IP address, right? There's no MAC address that we're talking about on the logical layer. We're talking about a logical address, an IP address. When that when that's checked with a subnet mask, it can figure out, this is internal or external. If it's internal, well, goes to layer 2, does the ARP, gets that information and can send it directly to the printer. But if it goes to layer 2 and layer 2 says, oh, no, hang on, this is not on the local network, then it goes a different procedure. Then it needs to go to the router so that can send that out. And you can see over here that once it's got the information that it needs, the physical information, then it can send that information to the destination. So an IPv4, the packet header looks something like this. Okay, you can see that there's a lot. Now, what do I mean by packet header? Look at this example that I have over here. These are just blocks that I bought to try and illustrate something. Okay, so a packet header, an IPv4 packet header, has different elements to it, just like you see there on your screen. Right up at the front, it will have a version. Now, I'm only really considering those kind of reddish coral color ones there. There are others, those yellow ones. I'm not really going to cover them. But if you look at that packet, okay, you have a little beast in the front. It could be the version, IPv4. That's what you'll be talking about. 0-100 in binary, made up of 4 bits. Then we have, let's go 16. Let's go to the one that says total length. So this is telling it, okay, so the total length for this whole packet is X amount of bits. Okay. Then we have protocol. Let's say the yellow one here represents the protocol. If you're using TCP, it would have number 6. So that would be in binary 6. If you're using UDP, then it would have, I think it's number 17 on there. Then you'd have a checksum. Okay, a checksum is to make sure that when the packet gets to the other side, that the machine there is going to check, do a calculation, and if it matches to this, it says that packet is great. If it gets a different value, it says no, that packet was corrupted, please send it again. Then it's going to have a source IP address, a destination IP address, and then it's going to have the payload. Okay, so you can think of this, a packet header looking at something like this, and that should make sense to us. So let's go for another minute or two, and then we'll have a break, and then after the break we'll come back and continue working on through this layer 2, because it is very layer 3, very comprehensive. It's interesting, and we need to spend time in here to understand it really properly. So for routing functions, we need to use, like I say, when we go outside of our network, we use things like a router. We normally talk about a router or a router. We also have, switches that do layer 3 routing as well. So let's look again to get an overview over here. I have a source machine. I'll have to read the IP addresses from the screen. So if you see my eyes go there, it's just because I'm reading. You can follow along with me on here. So I have a source IP address. I have a destination IP address. My network name, my street name is what? Well, 192.168.10, right? 10, that's it. Why is it a 10? Why isn't it a 0? Well, the name of the street is this because look, I got a /24, so it says the first 3 bytes. Okay, the first 3 bytes, they tell me what this network name is. So cool, I know what that is, and I'm on a /24. That's the network name, and this packet needs to go to, look here, I'm on 10.125. that's where I am, but where's the destination? It's on 30.11. It's not my network. It's a different network over here. So I have to go to a router, and the router says, okay, I know where that is. That's on another network. So I will send you, I know how to get to that router, and off it goes. So this could be even first floor, second floor in a building, right? You have people on the first floor, people on the second floor, you have lots of people here. Well, if you want to send to the print on the first floor, you have to go to the router, and then it sends you to the location that you need to go to. When the router receives the packet, the router receives the packet, looks at the IP, the address, the destination, it goes to check, is this internal or external, right? And this happens all at layer 3. If it's external, okay, send it off to where it needs to go. Routes, these are really important. Routes, routing are all about routes. So again, over here, if I need to reach this network here, 192.168.210/0/24 to 10.0/24, then I have to find a route, and my router is going to do that for me. So here I am, I go to the router says, I know about that particular network, and I know how to get to this router. This router has an IP address of 12.2, so it sends it to that router, and that router is connected to this network, or knows how to get onto this network. So routers are all over the networks, right? Are all over the internet. We use them. They are massively popular devices because they route information from your office to your ISP, and from your ISP they have bunches of routers, very high performance routers, to route all the traffic. Remember, at your house you might just have 3, 4, 5 hosts that are drawing on packets that need to go get the next 10 seconds of video from Netflix or whoever. But the ISP, your ISP, could be the same ISP for the entire street, and everybody might be watching movies at the same time. So the ISP has these routers that are capable of taking all of this traffic and routing them in all the right locations, and it does it via a routing table. And this is why some of these devices are so incredibly expensive, because these routing tables can be huge, and they need to build up a huge amount of information. You get different types of routes in the routing table: direct routes, indirect routes. So direct routes is when this router is connected directly to the next one, right? Or it could be even within a router between this interface and that interface. You even have default routes. And here is an example of a default route, which is a route of last resort. Not every router knows how to reach every network around the world. right? Because they would gather information from the routers that they have connected to. There are protocols that they would know. Oh, okay, I don't know how to get there, but I know that this router knows how to get there. Okay, so I know how to get to that router. So here we go. And then that router is concerned about the next hop and the next hop, and off it goes. So sometimes they don't know how to get there, and so we'll use what we call a default route, which is the route of last resort. So if you don't know this one and you don't know this one and you've never seen this one, then go here, which is just go out and find where is the best route for us to go through. So every router or every routing table is going to go and have one value. So this is the last slide before the break, and then we'll come back and I have a really nice animation for us to build through. Okay, so here we go. When a packet matches more than one path, so when you need to send a packet, you go to the router looks at its routing table and it says, ooh, you have a packet that needs to go out. I see that packet is 30.11. That's the IP that it needs to go out on. Let me look at my routing table. And it goes through the routing table and says, oh, I've got a default route, so if I don't know where to go, I'll go to that address. Okay, if I don't know anywhere, I'll just go to this address, and that could be your ISP, for example. It says, I know about this network over here because I've done that before, and that's the route that I use. That's the address. So if I need to go here, well, that's direct. These two are direct. I know about those. Those are interfaces that I have, so I know how to get there. Then I have this entry, which is also direct. And then I have another entry over here, and I know how to get to that particular location, right? So if I need to go to this destination, go here, 12.2. If I need to go there, go to this destination. If I don't know how to go anywhere, go to this particular destination. But which order does it use? Well, it uses this. It says, okay, when I need to choose which is the place to go to, the egress address, the next hop to go to, I'm going to use this set of rules. Number one, the longest prefix match. So let me go look at the first byte out of all that I've got. I need to go to 192.168. So the first part is 192. So I'll say, ooh, I've got 1, 2, 3, 4, 5. I've got 5 that have got that, the first byte. What about do any of them have the second byte? So, oh, 1, 2, 3, 4, 5 have the second byte. Oh, okay, cool. Then, do I have any one of them that match that third byte, the 30? And the first one down the bottom, no, that doesn't match. Oh, that one matches. Does that one? No, that doesn't. Oh, then I'm going to use this one. Longest prefix match. If they have multiple, then go to directly attached. So prefer directly attached rather than one that is next hop. So if I have a direct connection, go that one first, prefer that. Then use a static route, something that you would have typed in. So not that the router would have learned, you would have gone in there and typed it. So use that. Use the dynamic route, which is the one that the router would have learned automatically from talking to other routers. And then finally use, if nothing of those works, then use the default route. So let's have a break at this. This is a lot of stuff to get through. We will, after the break, we will come back and we will continue with an animation that I will build up, showing you step by step how you would send something from one network to another network. See you after the break. Watch, go have a, go drink something, whatever. There's some ads and everything coming up. Cheers for now.
My name is Chris Friends. I'm the AVP of Information Security for Interfaith Medical Center, And in terms of networking and security, we're widely known for being one of the first hospitals in the country to go zero trust. We're 6 sites, roughly 2,500 users. At the time, we had an older network. It was all Nortel switches. They were due for replacement, and we had evaluated a lot of vendors, and Extreme offered the best feature to price ratio for us. In terms of solutions, products, and services, we use Extreme switches for our edge. We have Extreme switches in our core and our data center. We also make use of the Extreme NAC and the Extreme IDS, as well as the Extreme Management Console. My favorite solution from Extreme is the NAC because it really has helped us achieve our zero trust strategy. Zero trust is basically the concept where you restrict all network communications to only communications that are essential for whatever particular device to function. If you just look at the news lately, you can see that there's been constant ransomware attacks against hospitals. One of the big ones was actually WannaCry last year. And one of the interesting things about WannaCry is it didn't only affect the PCs within hospitals, but within a lot of hospitals, the medical devices themselves actually became encrypted. And this is a huge patient safety issue, and as far as I'm concerned, it results in a whole new and wholly unacceptable meaning for the term denial of service. And it's obviously one of the things that we were very concerned with because protecting our patients is one of our top priorities. Flat networks allows attackers to laterally move through the organization and basically take a single compromised point within the organization and begin to spread it to more and more systems. And that's the kind of thing that we wanted to avoid. So we used the NAC to achieve a zero trust strategy where we heavily segment our network. In terms of the decision to go zero trust, I'm actually very big on testing security. So I had written a script that basically took a list of all the PC names within the organization, executed the script on a PC, and what the script would do is it would try to copy and execute that ICAR test string on each PC within the organization. And one of the things we found when we did this test is that the network segmentation we had in place at the time was actually very effective at mitigating the spread of this outbreak. We really wanted to build on that because it was so effective and increase the level of segmentation we had. So that's when we kind of began to introduce things like the network access control appliance, which allowed us to put policies in to even protect devices within the same VLAN or even on the same switch from each other. We have much less latency now than we had with some of the past switches we had. We've had a very good relationship with Extreme. We've had no issues with the support. It's always been very helpful. My favorite part working with Extreme was basically how they helped us implement the zero trust within our environment, how they came down and actually worked with us to achieve the goal that we had in mind.
Extreme Academy was created with one purpose in mind: to help educate and inspire the next generation of technologists and prepare them for the workplace. Through Extreme Academy, we are bringing our state-of-the-art training resources to innovative universities, colleges, and training centers all over the world. The Academy offers a hands-on, practical curriculum that gives students a foundation in the basis of networking, as well as advancements in artificial intelligence, machine learning, cloud, and automation. With this knowledge, they will have real-world skills and a true competitive advantage when they are ready to join the workforce, creating a much-needed talent stream for the industry at large, ready to take on the jobs of tomorrow. No previous networking experience is necessary to be part of Extreme Academy. All you need is a love of technology and a desire to learn. Students that complete Extreme Academy courses will be rewarded with an Extreme Networks Associate Level certification. This will help connect these students to their future jobs and help them stand out as they launch into their new careers. The Academy courses complement existing curriculums, and they are there to be taken advantage of by teachers. Courses can be integrated with existing lesson plans or be taught separately as standalone courses. Extreme Networks is an ideal training partner. As a leading provider of cloud-driven networking solutions, our technology provides the secure, reliable connectivity we depend on every day in our schools, in our hospitals, and retail stores, manufacturing floors, restaurants, hotels, sporting events, you name it. And with a fast shift to remote working and distance learning, our cloud-driven networking solutions are essential to ensuring business continuity in increasingly distributed environments, helping our 50,000 customers and 9,000 partners around the world to continue to advance how we live, work, and share. Extreme is continuously developing curriculum to keep up with the pace of our rapidly changing industry, and we're excited to bring our experience and expertise to all of you who are tasked with defining the future of work and what our increasingly connected world looks like. Getting involved is easy. All you need to do is register your interest on our website and reach out. Investing in knowledge is investing in yourself. Be part of Extreme Academy and get started today.
Some people have wanted to know those cars there, and planes. Do you build that? Yes, I'm a scale modeler, so I build those things in my spare time. Love building them. Oh, need to tell you, I got on my monitor here a little note during the break from Claire. Apparently, Charles Darwin. Oops. Just give me a minute, I need to close the door. This is a home studio, so the doors need to be closed. Oh, I was saying, apparently Charles Darwin didn't invent revolution. Apparently it was something called evolution. Sounds pretty revolutionary to me. Anyway, thanks Clay for letting me know. Okay, let's go back into this again. I said after the break we would go straight into here. Okay, so we got about an hour. Okay, let's go. So I'm going to build up this animation. It should be really interesting for you to see what happens in layer 3. Okay, so we've determined a few things already. We've said that layer 3 is going to work with logical addresses, IP addresses, and at that point it's going to know because of the subnet mask and which is the network. If that address is on the local network, the local street, or if it's an address on another in another location, in which case it needs to send it to the gateway, to that router, for that router to then handle it and get it out the door. So this example, I think, perfectly illustrates that. And I will kind of read a little bit off the screen because it's just impossible for me to remember all of these IP addresses. So if you see my eyes go in there, I'm just trying to be accurate as I read through. So we have a source PC, PC 15. It's on this network 10.1.10.0/24. So you know that the first 3 bytes over there are masked out. That identifies the network. Okay. We have a router. We're going to call it router A, and this could be the router in my house. It could be the router in your company, where all the network cabling, or not all the network cabling, but all the network congregate there as the gateway. So if anything needs to go out onto the internet, it goes through that router. And this router A, has an internal interface and external. Now, what do I mean by that? I mean, it has 2 network cards in it. Okay, one for the internal network and one connected to the external network. Okay, so it's a device. It's not a round device. It doesn't look round. That's just a symbol for it. But it has 2 network interface. And some of these could have more than that. But at its very basic, it's got 2. One for internal and one for external. The one that you have at home, when we finish this training, go look at the one in your house. And you'll see it's probably got like 4 ports, or 2 ports, whatever, for you to plug in, your home network to it. And then it's got 1 port that comes from the outside, from the phone line, wherever, and it comes into that. That would be the external interface, and the rest are the internal interface. That's the idea over here. I have another network over here that's connected between these 2 routers, router A and router B. This network is called 190.168.10. So you can see it's different to this one up here. Let me get the laser again. The laser went, there we go, laser green. Okay, so you can see this is 10.1.0/24. This one is 190.168.10/24. The 0 just indicates that's the name of the network. Okay, that's just terminology, how we talk about this. And this, you can see, is different, right? This is 10.1.10. This is 10.23. Completely different. Layer 3 means we need to use separate, a different mechanism, because this is not from inside our network. Okay. And again, router B has an internal and an external interface. This INT is not internal. It just means interface 2, interface 1, interface 2, interface 1. Okay, so let's see what's going on over here. If I look at PC 15, it has a MAC address, and there's the MAC address up there. It has an IP address. How do I know that? Well, if I type in Windows, if I type ipconfig, enter, boom, it's going to give me that address. If I type ipconfig space /ALL, it then gives me more information. It gives me a MAC address, an IP address, and default gateway address. So that's how you would do it. In Mac, it's if config, same type of thing. If config, Windows IP config. So there you have the IP address for this machine and the default gateway. So if you look at that, it makes sense, right? You're saying this is the MAC address, this is the hardware address, the VIN number, this is the IP address, the logical address that's been given to this by a DHCP server, and this is the default gateway. This is where you go when you don't know where else you need to go. You go to the default gateway. And I need to talk to a machine that's outside my network, that's on this network over here, 1023.0. I need to talk to this machine on this network. This machine also has a MAC address. It has an IP address as well, 1323.21. Actually, I think that is incorrect. I think that shouldn't be a 13. Oh my goodness. You know what? Even while I'm doing the presentation, I'm going to stop this and I'm going to fix that. It's not 13. Oops. It's 10, 23, 2. Destination is 10, 20. 3, 2, I think that's correct. 1023.21. Yeah, I think that's right. 1023. Yes, that's correct. So that's where I need to talk to. Amazing the things that sometimes come up when you're doing training. You do this over and over and over again, and you don't even see that. So okay, so we were here. We've looked at this. We looked at the default gateway. This had a default gateway of 3.54. Okay, right. Let's look at this router. On this router, we have the internal interface, and in the internal interface is saying we have. Let's go back to the laser, and let's go green. And we have here the MAC address of the router, yes, the interface, and then we have the IP address of the internal interface, the IP address or interface 1, if you want to call it that. That's the right way, interface 1, 10.1.10.1. That's the IP address of this, the interface 1. Interface 2 has another MAC address, you see, different to this one over here, completely different, and it has its own IP address, 192.168.10.1, for example. It would, it wouldn't be that, because if it's an external one, you're not allowed to use 192.168 as an external address. But for the purposes of this is what we're using over here. Okay, on this side, router B, the interface 1 over here has its own MAC address and an IP address, 192.168.10.2. Yes, 10.2. Remember the network name that connects them, 192.168.10.0. 10.0. So this is a subnet of 24, meaning the first 3 octets are masked. But look, the first 3 octets are all on the same network, so we know exactly how to get from there to here. The interface 2, well, that's got its own MAC address, and then it has its own IP address, 1023.254. That's this address over here on router B. Okay, so I've looked at this address. I've seen that the destination that it needs to go to is as follows. First of all, if I look at the packet header, there's the IP of the source, okay, of the source machine, PC15. There's the IP address that goes in the packet header. The MAC address, well, we know what that is, and that goes here in the source MAC address. So source IP, source MAC address. Okay, we're good with that. The destination is that IP address, and the destination MAC address is not this, right? This is not the destination MAC address. This over here, the destination MAC address, this is not going to go from here to here. This is going to go down this way up till there. So the destination MAC address for this packet, because it's not on the local network, is this MAC address over here of interface 1 on the local router. My little router sitting outside there, that's where it needs to go. Does that make sense? Now you might have a question, and that is, well, how do I know the destination IP address? I mean, how did I come up with this address? I'm glad you asked. We use a protocol called DNS. I'm going to cover it a little bit here, but I did record last week, and I've said this before, a 20-25 minute session on DNS where I go into much more depth. Go and listen to that and watch that. That's very, very good. Give you a really good idea what it is. In very short summary, I don't know what it is. I call somebody. I call another computer. I phone my ISP. I don't really, but I mean my computer phones them and says, hey, I'm looking for this, this person, this computer. Do you know what their IP address is? And that server then either finds out and comes and backs and tells me, or it might know what it is because someone asked it a few minutes ago, and then it gives me that output. So that's how I get the destination. But now we know it's on the external network. Great. We don't know the MAC address of that. We have no idea. But we know where we need to go. If we say, doesn't belong on our local network, so send it to the gateway. Send it to that default box. And what's the MAC address of that? There we go. That's what the MAC address is. So that's what it looks like. What does the routing table look like? Well, the routing table says, if you know nothing about where to go, the next place you go to is 10.1.10.0, which is what? 10.1.10.0. There it is, interface 1. So this is the default route. If I don't know where else to go, if I don't know anything about routes, go to the default one, this one. Off you go. That's where you go. And it says 10.1.10.0/24. That whole thing is directly connected. It's on my local network. Great. Absolutely. Fantastic. Okay. Now, let's move on and see what happens now. So now I've sent it to the router. The router looks at that packet, sees its destination, sees where it's supposed to go to, and fills in that information, right? There we go. The source IP is where it came from, 10.1.10.15. Destination IP, I've still got this as a wrong slide. Please forgive me. I'm not going to change them all now. Just know that is the wrong thing, and it's supposed to be 10.23.21. So there we go. Over here, the destination IP. And you know what? I can't let this go. Let me just fix this. 10, and I gotta go there and put 10. And go back. So sorry about this. Okay, so there we go. I have the source MAC address, which is me, right? That interface. And what's the destination MAC address? Well, the destination MAC address is this one here, interface 1 on router B, right? They're on the same network. They know this network over here. They know this network between them. They know the MAC addresses. So that's where I need to go. Makes sense? Remember, it doesn't know the MAC address of the destination. Doesn't need to know. Just needs to know the IP. Once it gets into here, then it will do an ARP broadcast, figure out where it is, and send it off to that machine. So I hope this is good for you so far. Let's look at the routing table. And the routing table is like it was on the first one. Well, I know about this network. I know about this network. I know where I need to go if I need to get to that particular network. So this is good, right? And once more, I need to change that and put a 0, and I think that is put a 0 here, and there we go. Okay, back again. So now same thing happens. What happened? There's a source Now there's a source IP, that's where it came from. Oh boy, destination IP 10.23.21. Source MAC address, well, it has its source MAC address, and it then has the destination MAC address. How did it get that destination MAC address? It did an ARP broadcast. Okay, it said, hey, who owns this IP address? If it's you, please send me your MAC address. And that machine, it was broadcast on that domain, on that network, on that segment of the network. The machine, who it was, that server, who it was, responded and said, hey, that's me, I have that hardware address. So it sent that information back, and eventually this packet made its way up into server 21. Is that clear? I know I do apologize for those little errors that crept up there, but I hope that that's clear, and you saw how the packet flowed. Even though it knew the destination was on the other side, computers still talk on layer 2 hardware addresses, so it had to go. It had to determine, layer 3 determined this is not from the local network, this is outside, so go to the router. From the router, it went from the internal interface to the external interface. Between those two interfaces, from there it went to the next point, to the next router, wherever that was. It could be the ISP, and from there it would have gone on and on and on until it eventually got to that company, to the router, behind that company or in front of that company, and there it got routed up, all the way up, did the ARP broadcast, and eventually got to that machine. Happy days, everybody was happy, and the message got through. It is a fantastic, absolutely fantastic system. It's just marvelous, a marvel of engineering. Now, IP addresses use DHCP. Okay, so like I said, your machine, you switch it on, it asks for an address, the DHCP protocol will send it to that. And generally speaking, that DHCP protocol is running on a server, a Windows server, a Linux server, and it's running as an application on there. So when someone asks, it gives out addresses as they need. Those addresses also have something we call a TTL. You might have heard of this before or not. TTL means time to live. That's how long those packets or that information is allowed to stay on for. So I think in Windows it used to be 4 days. So when a device comes in and says, hey, I need an address, the server would give that address. DHCP on the server would give that address for 4 days, and after 2 days it would come back and check, do you still need that address? Yes, I do. Okay, you can have it for another 4 days, and after 2 days it comes back and does the same procedure. So it can assign addresses dynamically as they need, as these devices pop up. It can also assign, you can also go in and assign addresses statically. So if you have a printer, you never want that printer to change IP addresses. That could be a problem, right? So what you do is you define and you say, no, I don't want DHCP to issue that. Although you can do it with DHCP as well. You can issue permanent addresses, but you might go in and type in and say, that's permanent address, never change that address. There's lots of devices like that you don't ever want the addresses to change. Routers are really one of these devices. When you switch them on, they are totally useless to you. They are totally useless. A switch, you switch it on, you plug in a cable, you plug in a printer, it works, right? You don't have to just plug it in, it works. A router, much more expensive devices, you plug it in, it's like it's does nothing. It waits for you to go in configure, and you can see from this already that you have to be really on your game to know routers, and that's why network engineers, good network engineers who know routing, get paid good money, right? Because this stuff is important, and you have to get these things right. So a router configuration is generally all done by somebody going in and typing and putting that information itself, and you'll normally have one address per interface. So static configuration is what you're going to have. So this is this protocol DHCP. I'm not going to cover it a lot. It's just good that you know what a DHCP is, Dynamic Host Configuration Protocol. It's a protocol that gives out addresses to computers that ask for it, for devices that ask for it. And those addresses will be IP addressing with a subnet mask, plus the address of a DNS server at the very least, plus a gateway. Generally, DNS servers, it will always give two DNS servers, a primary and a backup. So it would give something like 8888, which is Google's, and 8889, which is also Google's. So if one fails, it goes to the other one. But generally, it will always go to 8888. So there's all of this bit of information that it gives your client when it switches on its device. And like I said, it's all limited to a period of time. So this is kind of the workflow. So you switch on a device, it sends a DHCP discover. That's that message I told you about. Hey, I'm here. Is anybody here that can help me? Give me an address, etc. Switch on a mobile phone. Oh, yeah, this mobile phone is on. Is there anybody here that can help me? Yes, I can see you're on the O2 network. Just a minute. I'll check if you've got an account with us, blah, blah, blah. This is what happens. So I send the discover. The DHCP server sends back an offer. I send back a request, please give me that information, and then the DHCP server acknowledges that and sends me the IP address and everything else I need. That's why when you set up your little black box that you get from an ISP, when you set it up for the first time, you plug it in, the lights go red, they flicker, 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 boom, and then they go green. What's happening? Well, that box contacted the ISP and got information from the ISP, got its IP address, got its DNS service, got all of that, and then stored that in the config. So when you join onto that wireless network, or when you plug in a cable to that, it works straight away, because your computer doesn't know how to go to the outside, but it knows how to get to that box. Why? Because of DHCP. That box gave your computer the information that it needed. It's a brilliant system. It just cascades, and it's infinitely scalable. That's how you can have millions of customers at an ISP, or millions of customers at a mobile phone provider, and the system just works because of the way that it just scales so beautifully, so well engineered. Redundant connections, we've kind of spoken a little about this. In high enterprise or large enterprise, you wouldn't just have one router. Your ISP, I can guarantee you, will not have one router. It's just impossible. They will have multiple routers, and they will have them just for capacity purposes. But even if they were to have them for capacity, they would also have redundant routers. So they would have, like, instead of just having one, they might have 2 or 3 redundant. So if one fails over, the other one takes over. And this can bring issues to do with loops and stuff like that. But there are lots of protocols that handle these things. Also, if a packet with a TTL is sent, every router that it hits, that TTL is decreased by 1. So if it just carries on going around in loops and loops and loops, then between the routers, then what happens is eventually that TTL reaches 0 and they just drop it, so as not to affect the rest of the traffic that is using routers. So I hope that has been really useful to you. Is there more to this? Oh yes, there is. Is there a lot that I can learn on this? Oh yes, there is. I've really covered the basics of layer 3. It's such a fascinating topic. Don't let it die here with me and say, okay, I now need, Isaac has taught me everything I need to know about layer 3. Of course, your job might mean you don't need to know much of this, right? You'd like, as long as I know what it does, that's enough. And that's great. But if you're really looking to have a career in networking, then immerse yourself and learn more about this, because it's so interesting. And with that, let's go to layer. This is the wrong layer because of the order that I done it. So let's leave it quickly here. I'll take a quick switch over break, and then I'll move to where I need to go. So just give me a minute, and okay, here we go with layer 2. Layer 2. We're tracking well, we're on time. Let's see how we go. Let's read again what we're going to talk about here. Layer 2. Understand the principles of data link layer. Understand L2 addressing. By the way, I like data link layer because if layer 1 is the layer on which the Ethernet cable, the highway, the railway tracks, if that's layer 1, then this is the layer that links into that, the data link layer. So I like that term. I think it's really appropriate. Understand layer 2 addressing. Understand fundamental switch operations. Understand the separation of broadcast domains using VLANs, which is a new topic that we haven't spoken about before. Let me change my laser color again. I like the green. It tends to stand out quite well. Okay, so data link layer. Devices that use the same medium, a cable, etc., might want to send signals at the same time. These signals, of course, we know can get corrupted, right? And the example is like if you're on that side of the street and I'm on this side of the street, and we look at the traffic, we look, and then we both cross at the same time, we might bump into each other, right? Corrupting the transmission. This means that this type of environment is called a collision domain. It's kind of like it is in a real world environment, right? I live quite close to a school, and there are generally lots of kids in the morning riding bicycles, walking, etc., and it opens up itself for collision. Traffic has to be really slow. It's like 20 miles an hour, and there's red lights and there's all sorts of things to slow things down because of the possibility of a collision. And you know what happens when a collision happens? Everything stops. Traffic is a nightmare, ambulance, everything. And in networking, it's not that much different as well. You also have these collision domains. So when we're talking about Ethernet and things like this, we're really talking about collision domains. And if you think about walking along a busy street, I think it was about a year and a bit ago, I went to Shanghai. I had the privilege of going to Shanghai to go do some teaching in Shanghai. And there's a very famous scene that appears in many photographs when you look at the new Shanghai and you look at pictures taken from the same location years ago, 20, 30 years ago, and it was nothing. And now you look at it and there's just these incredible buildings. I wanted to go and take my own picture there. And when I got there, the pavements, the sidewalks in Shanghai leading to that particular platform where you can look onto the city, they are so incredibly wide, wider than I saw in Fifth Avenue in New York. And I couldn't understand why on the one side of the of the street everybody was walking in this direction, and on the other side it was hardly anybody walking in the other direction. So I kind of hopped across and thought, oh, this will be a lot quicker because of so many people. And when I got there, a policeman said to me, in Chinese, which I didn't understand, but I understood from his finger language, like, telling me to go to the other side of the street. Just the amount of people. And that was a perfect example of a collision domain, right? So many people on the sidewalk at the same time means that everything slows down. It's inevitable. There's collisions. You bump into people. You bump into, it's people bump into you. Ethernet is a lot like that, because there's just so many millions and millions of packets that need to go on and travel on a network. So this picture, I've been to this particular location. You understand what we're talking about when we're talking about a collision domain. It's generally spoken of as a physical segment. So a collision domain could be a LAN, right? It could be a LAN, and is a LAN within your network. That's a collision domain. It might be extended, so you might be on the first floor and there might be another switch on the second floor or whatever, and you extend this domain using a cable and a switch. So it might be extended across different platforms. In the old days, we used to use hubs. They were like a little, a bridge just to connecting, and that all that did was that just extended that domain, that collision domain. So as long as you have an idea what we're talking about when we're talking about collisions and domains. So here you'll see in a domain up on the top, LAN single segment collision domain. So small segment, number of different computers on there. They're going to have collisions between them. If you hook up two offices together with some sort of a bridge function like a hub or something like that, then all you do is you just you increase the amount of collisions that are going to happen, because you've just increased your domain. Now, I used the example earlier, and I spoke to you about this protocol called ARP. So ARP is one of those protocols that needs to shout. So imagine somebody walking into the office, and we kind of covered this a little bit in layer 4 where we spoke about TCP and UDP. If I walk into the office and I need John Smith, but I have no idea who John Smith is, I can take a loud hailer and say, "Can John Smith please stand up?" What happens when I do that? When I do that, everybody in that office hears me. John Smith responds. Yes, everybody heard me, but John Smith is the guy who responds. And so it's a broadcast. I broadcast my message to everybody. Oftentimes when I go to companies, and I used to travel a lot more, and I'd be teaching, and then they would inevitably have a fire alarm. And so the alarm bell goes off, or they make an announcement and say, "Please ignore, we're testing the alarm," etc., etc. So when they do that, it's a broadcast. They broadcast that announcement to everybody, and that's what ARP does. It's a broadcast, and everybody on that domain, every device on that domain, boom, gets alerted. Hey, somebody wants to know something. So if you have two LANs and you join them with a bridge, and this one had 50 computers and this had 50 computers, then when you do a broadcast, all 100 computers get that ARP broadcast, right? So if your network was 400 or 600 or 1000, imagine, you remember we were speaking about the slash. If you had a slash, 16, if you had a /16 networks, imagine how many broadcasts that would happen. If you just had one massive domain, 16,000 computers, you do one broadcast and it goes to 16,000 hosts. So you understand that what the broadcast domain actually is. Now, switches have been fantastic. The switches that we make, that other companies make, they have been really fantastic, because switches reduce the clashes significantly, because you have a direct connection to you and that switch has the intelligence to only allow ARPs when it needs to, and because it also builds a table of information in there. So by building a table of information, it knows how to get you just ARPing between yourself and the switch. The switch then doesn't have to ARP to everybody else, because it has the information that it needs. So switches have really revolutionized these domains. They're still collision domains, but been able to reduce that completely. Now, where layer 3 was logical addressing, IP addressing, layer 2, a lot of that is translating that IP address into a hardware address. Remember, devices on the same segment, on the same LAN, on the same street, everybody, every neighbor in the street, we all talk the same language, right? We all in the same boat. If one of us loses electricity, everyone loses electricity. If the fiber cable to the street is cut, we all suffer together. There's no more internet connection, right? So the MAC address is the hardware address. So translate this IP address into a hardware address. It has really three functions. This hardware address. The first one is the hardware address enables us to talk directly to a machine. Now the hardware address looks like this, right? It is made up of 6 bytes. Now this I haven't covered to you and covered yet, and there's going to be a bonus lesson over the December close holiday period, Christmas period. There's going to be some bonus lessons, and this is going to be one of the bonus lessons. Up till now we've been doing everything in binary, just talking about binary, but now there's another system called hexadecimal, and where binary is base 2, hexadecimal is base 16. Okay, base 16. Very interesting. And this is how we write in base 16. This is how we do it. We write with numbers, a combination of numbers and letters. I'm not going to cover it now. We don't have time to do that. But this is how we do it. This is 6 bytes. So I could translate this from hexadecimal to binary. But you can see how long this number would be if I did that, right? In binary, it's huge, absolutely huge. So we shorten it by using hexadecimal. So this is what a hexadecimal number looks like, and that's the number that's burnt into your phone and actually looks something like that. The first 3 bytes, they tell you the manufacturer. Okay, what the manufacturer is, who the manufacturer is of that network device. So you can do yourself as a little example. You know what? Maybe we'll leave it up on the screen. We'll have a little thing on the screen that will give you a little exercise to go do. So the first 3 bytes tell us who the organization is that stamped this number on there, and then this part is the host ID. Okay, the identifier for that. We also use MAC addresses to broadcast, right? So F is the equivalent of in binary 1111111. Okay, that's the equivalent. FF is 111111, but this represents this represents all 8 bits switched to 1. So that's the multicast address. So sorry, the broadcast address. When I walk into the office and I shout, "Where's John Smith?" I'm using a broadcast address. This is what it looks like. And then I have something they call multicast address. So unicast, I talk to one. Broadcast, I talk to everybody. Multicast, I talk to a group of. And I use a multicast address to be able to do that. So each device that's attached to that network has to process that broadcast packet. Okay, so as broadcasts increase, and ARP is not the only broadcast, but as ARP increases, then performance goes down. Just think of this example, this lady here with a megaphone. One of the times I was teaching in Singapore, they had a fire drill, and so every floor and every company had their own officer, and each officer had one of these bullhorns. You can imagine Singapore is a very organized place, but when you have everyone with a bullhorn, it's a little bit of a problem, right? But you get the idea. So here's going back a little bit to our Ethernet frame. Ethernet frame, we call that Ethernet frame version 2. Destination MAC address, We know about that. It's made up of 6 bytes. Remember the 6 bytes, the hexadecimal? There it sits right at the top. Let me go there with the laser again. There's the destination MAC address. There's the source MAC address, right? The destination and the source MAC address. This is, what type is it? IPv4. Well, we write it like this: 0 by 0 800. The payload, you remember the payload, and then we've got something we call padding. So this is really interesting. I'm going to tell you a little bit about padding. So each Ethernet frame has to have a minimum size of 64 bytes. Okay, that's the minimum size. But imagine somebody says to you, remember in the example in the first one, somebody says pizza, sends you a message saying pizza, and you respond with the newest, shortest word in the English dictionary, which is K, right? You don't even say okay anymore. We just say K. Pizza, K. K is a very small, it's one letter in ASCII that fits into 1 byte. But the Ethernet frame needs to be 64 bytes long. So what's going to happen? Well, when you get to the payload, it's going to be absolutely tiny. What you going to do with the rest? We pad it. And what we do is we just keep on padding it with zeros. We just fill it with 0, 0, 0, 0, 0, 0, 0 to make up that 64. Okay, make up that 64. And after that we put a frame check sequence. That's like that checksum that we put in there, and that's used like a calculation, so that when I send that, I put a value inside there, and I whatever that value is, it could be a 0 or a 1. And when it gets to the other side, the computer checks and does that same calculation, and it needs to match that frame check sequence. And if it matches, it says, okay, there's integrity on this, it's fine. If it doesn't match, it drops and says, hey, can you resend that again, please? So switches, they have in them something called MAC forwarding tables, okay, and they use these forwarding tables to build up knowledge of everything that is connected. So let's take the example in a network where you have, say, 16 computers connected via cable, 16 computers, 4 phones, 1 printer, connected via a 24-port switch. All of these are connected. You're the network engineer, you've come in here, you've just set the whole thing up, and you switch on all the computers, and you switch on the switch. The switch has, at that stage, even though it can work, it's got nothing in its MAC forwarding table. It doesn't know which computer is coming in on port 1, which is on port 2, which is on port 3. It has none of that information in it, and it needs to build that information. So as I start sending packets from one machine to another, from one machine to a printer, the computer needs to respond, the switch needs to respond, and it starts building its table, but it doesn't know. So these broadcasts go out, and when these machines respond, when a computer responds, it has its source IP and its MAC IP address, and it sends that information back through the switch, and the switch then fills in that data in this forwarding table, right? It starts building out this forwarding table. It says, oh, okay, this computer A wants to talk to that computer on that side. Cool. I know its destination. I know its MAC address. I know its IP address. Cool. It wants to talk to that computer. It broadcast. That computer said it was it. It gave its MAC address. It came back through the switch. I will add that into my MAC table, to this Mac forwarding table, and now when that computer wants to send again to there, I already know what that information is. I know on which port that printer is connected, which port that computer is connected. So now I don't have to keep on broadcasting to everybody, because in my Mac table I have that information. So clever. When it does need to flood, when it does need to do a broadcast, the machine that needs to do that broadcast will broadcast that. If the switch doesn't know about it, it will flood every port. So every port that has a cable connected to it, it will flood that port with a broadcast and say, hey, this takes priority over here. Someone needs to know an IP address or a MAC address for this IP. Tell me who it is. And once they tell it, then it stores that information. So you can see how really big switches, expensive switches that have these MAC tables in them, they can get very, very, very busy, right? As tons and tons of traffic, get 24 port, 48 port switches that connect to other switches. They are linked together. So these MAC tables can get bigger and bigger and bigger, and they need to process them. So you can see what happens when you go in and you decide, let me just switch this switch off. Let me just power it off. Those MAC tables, most of these switches, when you switch it off, it loses all of that information. And then when you switch it on, it has to rebuild all of that information again. So very, very interesting. I don't want to spend much time on here, but let me talk a little bit about a concept we haven't really spoken about before. You might have heard people talking about VLANs, V as in Victor, VLANs. And like in anything in computing nowadays, a VLAN stands for a virtual LAN, a virtual LAN. So you might be thinking, okay, so virtual LAN, we've been talking about physical LANs up until now. Now, virtual, what does a virtual LAN mean? Well, think of a situation like I have on this slide over here. Up here, I have, let's say, an accounting department. And underneath that, I might have a HR department. And here I have a finance department, and over here I might have research, and here I might have production, right? And all of them are connected into the same switch. I've got a 48 port switch, or 2 or 3. I've stacked a whole lot of them together. That means all of those domains are, there's broadcast going on, there's traffic going all over the place. So someone came up with the idea, like, what if we could segment those, and within the same switch, if we could, kind of, so imagine taking everybody in finance and taking their network cables and saying, okay, so plug it into 1, 2, 3, 4, 5, 6, 7, 8. So the first 8 are for finance. The next 8 are for HR, and the next 2 are for R&D. Well, it's not really going to help you, because it's still one switch, and so broadcast traffic still goes to everywhere and everyone, right? So the idea was, okay, so what if we, inside that switch, what if there was a way that we could tag traffic, so that when a packet comes from HR, it could say, hey, I'm a HR packet. I'm a HR packet. And what if we could do that with all the HR packets, right? Then, if we could do that, then we could virtually separate the HR packets from all the R&D packets, from all the accounting packets, from all the finance packets. And so, in a physical switch, we would have virtual LANs, and broadcasts would only happen. So somebody does a broadcast in the finance department, it only broadcasts in the finance. Someone does a broadcast in the HR, it only broadcasts in the HR. That would mean that we could have a massive layer of efficiency. We could do some really cool things in terms of broadcast, but in terms of efficiency, in terms of security. Why should people in operations be on the same network as someone from HR, right? That's a good idea. Well, you could do it by buying 2 separate switches, and hooking these people up. But imagine if you had 20 departments, you'd have 20 switches to do that. That would be a mess to configure. So in one switch, you can segment your network using VLANs. And by doing that, you make a very efficient network. Now, an Ethernet frame will have a special tag. If you have VLANs, and most switches, certainly enterprise switches, have the ability to do that, to tag a VLAN. Think of it as tagging it like a flag, like a color. Then it inserts something new into your Ethernet frame. Okay, it's called an 802.1q. That's one of these standards the IEEE came up with. Field, and that field has some information. Okay, that's a tagging field, and it has a tag number. So we don't tag them with colors, we tag them with numbers. So we'll say something like, okay, let's put all of HR onto VLAN 5. Let's put all of finance onto VLAN 8. Let's put all of production onto VLAN 20. And you can have about 4,095 different VLANs if you really wanted to. But here is that VLAN tag. So you look at the Ethernet frame like we've seen before. You'll see it's still got the destination and the source MAC, but now because you've enabled the switch for VLANs, here's that little tag that gets inserted into that frame. So that's like me having this Ethernet frame, taking this out, separating this, adding another piece here, another, I don't know, a black piece for example, and then plugging that back in again, and now this identifies to the switch, this particular packet is a VLAN packet, and it has on its ID VLAN 10. So cool, I'll chuck it into VLAN 10. That way, if it has a broadcast, it only happens in VLAN 10. Does that make sense to you? Yeah? It's very, very cool feature. And if it needs to do a flood, like I say, it floods a broadcast, it only does it within that VLAN tag. These are a lot of things. You can come back here later and read these slides because they contain quite a lot of information. Again, loops, we've chatted about this thing before with the issue of loops, how switches have technologies inside of them to prevent loops from happening. Companies like us have developed special protocols to avoid these loops from going round and round and round and round. So you could have loops on routers, and there's technology there to prevent those from happening, like the TTL. So every router that it hits, it just counts down. When it gets to 0, it just drops a packet. Or here there are other protocols, lots of other protocols that will allow us to then just kill that port on that switch that's causing that loop until we figure out what it is. So loops need to be avoided. This comes from experience and understanding networking. So let's finish off by just showing you some of those protocols: ELRP, SLPP, EAPS. These are some of the different types of technologies. It's just too much to go into every one of these and try and cover all of these in this particular session. So remember, we're talking about layer 3, layer 2, layer 3, layer 2, layer 3 logical addressing. It uses IP addresses to ensure that a packet can get out onto the internet. Layer 2, well, it takes that IP address, and what it does is, if it's for the local network, it sends out, it does an ARP to try and figure out the physical address and then sends it to that. If the packet is to go outside, the physical address is the physical address of the gateway, of that default router, and it sends it out there, and then the router from there starts to look at its routing table and starts to figure out the path to go to get to its final destination. It is so interesting. I urge you, don't stop here. Go read more, because this is a fascinating topic. And finally, I want to show you this slide, which is about different switches. We've shown you a slide like this before. This just happens to be a switch. Look at that beautiful purple in the middle there. I mean, those are just awesome. To see purple in your server room, mwah, wonderful. But you'll see on the right hand side, we've put about some specifications for each one of these switches. By now you should be able to see, okay, this is series 220. You can see it's a 24 port. You've seen that before. 10 gigabit Ethernet. There's two of them. So, okay, there's two of those ports. Cool. This is a gigabit switch. You'll see that this can handle 16,000 MAC addresses. All right. So it can handle 16,000 MAC addresses. It can do 1,024 VLANs. Right. It can do 88 gigabits per second and 65 Mbps. I'm just trying to think. I knew what that was. Forwarding performance, packets per second, how many packets per second it can handle. So that switch can handle 65.5 million packets per second. You think, that's crazy. I mean, that's just unbelievable until you go down and look at this one. Look at this switch over here. Its capacity is 880 gigabits per second, and it can handle 714 million packets per second. Insane. This is why you pay for some of this equipment. So the number of VLANs supported, that's of course one of the reasons that you find such discrepancy in costs. The number of MAC addresses supported, the switching capacity is how much switching capacity do you have across all of these? How much throughput can you put through all of these switches? And then how many packets can you do at any single time through these switches? And then there's other bits and pieces that get added. Automation, how you automate it, how you manage them. This is just a little example over here. So in this one, I'm going to kind of read it, but you can read it yourself. Switching capacity refers to, you can see on the top on 88 gigabits per second, how much bandwidth is provided by the hardware. And there we take the port, how many ports? 24 times 1 gigabit per second times 2. Why? Because it's bidirectional. It talks and listens at the same time. Plus 2 gigabit ports, right? 10 gigabit ports. And again, they're bidirectional. So we multiply by 2 and we get a round figure of about 90 gigabit per second. That's how much throughput, right? Switching capacity. And then performance in packets. How many packets per second? Well, you can see we're talking about 65.5 million packets per second. Insane, absolutely insane. So, I think we've come to the end of this whole session. Layer 2 and layer 3, we covered a lot of material. Read more. There's so much to learn. TCP guide, remember I mentioned that the other day. TCP guide, I think it's tcpguide.org, a fantastic resource for you to go and listen to and read. There will be further resources that will be popping up as we go along. This is the last lesson that we're doing for 2020. Let's get rid of 2020. We've just all had enough of 2020. But this is the last one. We will start again in January. I think it's the 6th or so of January. We will start again. But I'm sure there'll be an announcement about this. Let me just say a few things. Thank you for joining us. Really appreciate it. Please post comments. You know, I'm happy. You'll see I'm on YouTube, so if you post on YouTube, I will respond to you personally, not just on Extreme. I will respond to the comments on YouTube. Interact with me on LinkedIn if you want as well. Thank you for attending. We've gone through 3 lessons. That's 6 hours of training. We've done a lot of stuff already. You already should have a totally different vocabulary, a totally different approach to this to networking, and I hope it's given you the confidence and the encouragement and the stimulus for you to come back again. Come back again in the new year. Don't falter by the wayside now. Come back and finish. Go to the to all lessons and go get your certification. Thank you again for joining us. Absolutely love you all. Absolutely love teaching. Hope that you've learned. See you in the new year. Ciao.